Here we continue our work on function analysis with these accumulation functions, but we're giving them graphically now instead of algebraically. Our logic is exactly the same, and we're going to need all of these same facts and definitions that we've been using throughout the class. So make sure you have your notes handy on these because they will be a helpful reference. If you don't have notes, now would be a great time to copy these down. Okay, let's look at our first example here. And the last sentence in these, so we don't really care that it consists of line segments and a semicircle. Okay, here's our semicircle, here's our line segments. Doesn't matter, right? G is given by this function. We don't necessarily care about the bounds. We just note that it's an accumulation function, and we want the values where G has a horizontal tangent line. Okay? So you know a horizontal tangent line is equivalent to, just like we've been seeing before, horizontal lines have zero slope, so we want the derivative of G to be equal to 0. Well, the graph of f is the derivative of G, right? Well, let me rewrite that in a more rigorous way. So G prime of x, remember taking that derivative cancels out this integral operation, is equal to f of x. Okay, so we want f of x to be equal to 0. And we see 2 points, so that is true at x equals -1, and that is true at x equals 5. Okay, you may be tempted to include -9 and 9. Do not include those points. There's 2 reasons. The first reason is that it's not included in the intervals given because they didn't put pointing brackets, right? They put parentheses. The second reason, though, the more important reason, is actually the derivative is not defined at those points because the function is no longer defined to the left and to the right. Okay, so the derivative does not exist there and does not exist there. So we only want to include those 2 middle points. But that's it. Well, that's all we're doing. So we're interpreting what it's asking us for based on these definitions and then finding the points where those are true. We'll look at a couple more examples, but that's pretty much the whole lesson. Okay, here's another example. The graph of f is blah, 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 made up some shapes. We don't really care that much. G is given by the integral from 9 to x of f of t dt, and we want to know where G is decreasing. Well, let's think about what that means. G is decreasing means G prime is less than 0, and G prime of x, well, that's really just f of x. So we want f of x to be less than 0. Well, looks like there's a couple intervals that I see here. So it looks like from here to here would be my intervals where f is less than 0. So I'd say, and because they asked us for open intervals this time, I would say, or sorry, those are closed intervals, pointing brackets, right? I would say from -9 to -6, new brackets, and -2 to 7. Okay, so again, we're taking a derivative and we're figuring out what the text is asking us to determine about the derivative. Here we want it to be less than 0, so we find those regions on the graph. Okay, here is where these get tricky, I think. G is concave down is what the text is asking us, and it of course tells us that the graph is made up of some shapes and that G is this accumulation function right here. So G is concave down. We could go back up to our reference. What this means though, G is concave down means G double prime is less than 0. The second derivative must be negative. Okay. So don't be tempted to look at the concavity of this graph because remember this is not G, right? We need to do a little bit of thinking here. So G prime of x would be, because this is an accumulation function, f of x. G double prime of x would be f prime of x. So we want f prime of x now to be less than 0. F prime is less than 0. So it's not where the graph is less than 0 because the graph is f and not f prime. F prime is less than 0. This means that f is decreasing. Okay? So we want all the intervals where f is decreasing. So that's anywhere we're going downhill on this graph. So that's here, here, and here, right? So our concave down intervals, and we should be very specific here, so g of x is concave down on -9 to -8, it looks like. -7 to -3, and 6 to 9. So you can think of it as like the accumulation function kind of removes a step, right? So being asked for concavity about this graph really has to do with the derivative of this graph. The surefire way to get it is to write out this every single time, and this will help clue you into exactly what you should be looking for in this graph. As always, double check your understanding before you move on from the video. Make sure you have good notes and then jump into the problems.